We discussed the properties of immersions. Now let's discuss the properties of submersions. Here we have the definition of a submersion. We consider a differentiable map. We say that F is a submersion at a point X if the differential of F at X is surjective. Okay? And we say that F is submersion if F is submersion at every point. Again, let's point out that there are restrictions over the dimensions of our manifolds in order to have submersion, because this linear map over here, in order to be surjective, we need at least that the dimension of the target space has to be less or equal than the dimension of the source. But the dimension of this space is the dimension of n as a manifold, and the dimension of the tangent space of M at X is also the dimension of n. So if F is a submersion at a point X, what we have is that m, small n, is greater or equal than small n. Okay? If m is equal to n, then F is a submersion at X if and only if F is an immersion at X. Okay, again, if the dimensions are the same, F is an immersion at X if and only if F is a submersion at X. We have a local normal form for submersions that, again, it's essentially the same result that we already know from the curses of analysis. Okay, what the theorem says is that if we have a differentiable map and a submersion at a point X, then there exist local charts, phi defining a neighborhood of X in M, and psi defines in a neighborhood of the image of X by F in the manifold M, such that the local expression of F in these charts is this map over here, which is sending the vector x1, x2 till xm to its n first coordinates. Let's remind ourselves that m is greater or equal than n. Okay, how do we prove this? We are in a similar situation as in the case of the local normal form of immersions. Okay, it's more or less the same picture. Here we consider phi, psi. Okay, here we have the local expression. And what happens is that F is a submersion at the point X if and only if the local expression is submersion at the point phi of X. But we can apply the local normal form of submersions to this map. Okay, so again, we are going to have here diffeomorphisms, alpha defined in the neighborhood of phi of X, and beta defined in the neighborhood of the point here, psi of f of X, such that the map that is closing the diagram is actually the map that we considered in the previous slide. It's the map that is sending x1, x2 till xm to its n first coordinates. Okay, and again we have we make the same argument that we did for immersions, and the argument is that the composition of phi and alpha is a local chart, defined in a neighborhood of X, and that the same thing happens with beta, with the composition of psi and beta. This is a local chart defined in the neighborhood of f of x. So now the expression of f in the local charts, phi composed with alpha and psi composed with beta, is exactly this map over here. So as in the immersion case, the theorem that we already know for Euclidean spaces gives us the local normal form of submersions for the more general setting of differentiable maps between abstract manifolds. Okay, so this is the result that we are studying right now. And what happens is that the preimage of f of x0 is a submanifold of dimension n minus n in the neighborhood of x0. Sure, if you fix here some coordinates, what is going to be in these coordinates the preimage of this point? It's going to be the product, how can I, yes, the product of the set consisting only of this point and r to the m minus n. And so yes, it's in local coordinates, it's clearly a submanifold. And since this is the definition of submanifold is actually introduced by using local coordinates, then the preimage of f of x0 is a submanifold of dimension n minus n in the neighborhood of x0. That's a direct consequence of the local normal form for submersions. Okay, what happens if we consider y, a point in n, and we consider the preimage? Is the preimage going to be a submanifold? And since being a submanifold is a local property, it's going to be a submanifold if it is a submanifold in the neighborhood of every of its points. So we just need to require that f is a submersion at every point x in the preimage of y. If these things happen, then the preimage of y is a submanifold of m of dimension m minus n. Okay? So right now, in order to work with this setting, it makes sense to define the good points and the good values. We say that x is a regular point if f is a submersion at x. These points are good because the preimage of f of x is going to be a submanifold in the neighborhood of x. We say that y is a regular value if all points in the preimage are regular. And a point is critical if it's not regular, and analogously, a value is critical if it's not regular. Okay, so in the previous slide, we said that the preimage of a point in the manifold n is a submanifold of m of dimension small m minus small n if f is a submersion at every point in the preimage. But if we just take a look to the definition, that's the same that's saying that y is a regular value. So that's it. If y is a regular value, then the preimage of y is a submanifold of m of dimension small m minus small n. In particular, it is manifold. Okay? And something that it is very interesting is that since it's a submanifold of m, we can define its codimension. The codimension, by definition, codimension of the preimage of Y, but the codimension of every submanifold is the dimension of the ambient manifold, which in this case is M, minus the dimension of the submanifold. And what you're saying is that the preimage of Y is a submanifold of M of codimension N. Okay? Now we are going to see several examples. The first one is going to be not so interesting. The second one is going to be more interesting. And the last one, probably even more interesting. The first one is the sphere. Here it's a word in Portuguese. Sorry, I forgot. The sphere. We have, consider this map, the map from R to the n plus 1 to the line, such that the image of the vector, of a vector is indeed the square of the distance to the origin. This map is polynomial, it's infinity, is of course real analytic. We want to calculate the critical points, but okay, we can consider the differential of f at a point. And since we are already working with Euclidean spaces, we can consider the Jacobian matrix. And the Jacobian matrix is going to be a 1 times n plus 1 matrix whose entries are the partial derivatives of f. So we are going to have here the 2 times x1, 2 times x2, and the last one is 2 times xn, where x is x1, x2, and so on. What you get is that this matrix defines a linear map between, well, here is plus 1, yeah? Okay. A linear map between R to the n plus 1 and R. And in order for this map to be surjective, you need the rank to be maximal. And this happens whenever there is one of these, let's consider like this. This happens whenever one of these coefficients is different than 0. So what we get in this way is that the set of critical points consists only of the origin, because this is the unique case in which this matrix is the 0 matrix, and in that case the differential is not surjective. But there is no any other critical point. And the regular values are the images of the critical points. The image of 0 is 0. So if we consider here the set of critical values, this set has just one point, the 0 point of the real line. And so if we consider the preimage of any point different than 0, that's going to be a submanifold of R to the n plus 1 of codimension 1, or in other words, of dimension n. And so we get that the n-dimensional sphere is a real analytic manifold of dimension n. Of course, this is not true for the critical value. The preimage of 0 is a point, and that's not going to be a manifold of dimension n. It's not going to be a submanifold of dimension n. So it is fundamental that we do things right and we apply the theorem just to regular values. Okay? Let us consider now a new example, the so-called orthogonal group. Okay, so the orthogonal group is the group of matrices that preserve the usual scalar product in Rn, and it can be given by that matrix equation. The orthogonal group consists of the matrices n times m such that the product of the matrix and its transposed is equal to the identity. Let's point out that that implies in particular that A is a regular matrix because the determinant of this matrix is the square of the determinant of A, and it has to be equal to 1. So the determinant of A is either 1 or minus 1. In particular, it is non-zero, and so A is a regular matrix. Okay? And it's not difficult to prove that the orthogonal matrix actually are forming a group, that the product of orthogonal matrix is still orthogonal, and the inverse of an orthogonal matrix is also orthogonal. Okay. Let's point out again something else, is that this equation is homogeneous in the entries of the matrix, but is homogeneous of degree 2. It's not a linear system of equations. We can consider a simpler group, which is a group of symmetric matrices. The matrices such that they coincide with their transposed. And this is much simpler. In particular, you can see that this is a linear equation or a linear system of equations. And indeed, something that happens is that if you consider one of these matrices here, and you consider the elements that are in the principal diagonal of the matrix or above it, then these elements determine the symmetric matrix. For instance, let's consider a trivial example. If we have these elements over here, there is just one way of completing this matrix so that it is symmetric, and it's just writing there a 2. So Sn is a linear subspace of the vector space of square matrices, and indeed it is very, very easy to calculate the dimension because you have just to sum the number of elements in the principal diagonal, that's n, plus the elements that are in this subdiagonal, that it is above it, immediately above it, that is going to be n minus 1. For the example, that's everything, but for a general n times n matrix, you have to keep going till you get to 1. And this is n times m plus 1 divided by 2. So that's going to be the dimension of the group of symmetric matrices. Again, it's not difficult to prove that the set of symmetric matrices is a group. Okay, it's a manifold of that dimension. We want to use what we know about submersions and regular values in order to show that the orthogonal group is a submanifold of the manifold of square matrices. Okay, so let's go. Let's define this map that sends a matrix, a square matrix of dimension n, to the product of A and its transposed. And I wrote here that the target space is the symmetric group, because it is. Okay, what happens is that if we consider this product of A and its transposed, and we transpose, the transpose of a product of a square matrices is indeed the product of the transpose, but we have to invert the order. So it's going to be the transpose of the transpose of A times the transpose of A, and the transpose of A is A. So in particular, this proves that this matrix over here is symmetric. So F is a map, a differentiable map, between square matrices of dimension n and symmetric matrices, right? And the orthogonal group is just the preimage of the identity. So what we want is showing that the orthogonal group is actually a submanifold of the manifold of square matrices. And in order to show that, it's sufficient to prove that the identity is actually a regular value. Okay, so let's do that. Here we have, again, the definitions of the orthogonal group and the symmetric group. And the proposition is that the orthogonal group is a real analytic differentiable manifold of dimension n squared minus n divided by 2. Okay, so before getting into more details, what we want is actually showing that the identity of that map F that we were considering in the previous slide is a regular value. If that's the case, then the orthogonal group, which is just the preimage of the identity, is a submanifold of the manifold of the square matrices of codimension, and the codimension is just the dimension of the target space. The target space is the manifold of symmetric matrices. And we saw that the dimension of Sn is indeed n squared plus n divided by 2. Since the dimension of the set of square matrices of dimension n is n squared, that implies that the dimension of the orthogonal group is going to be n squared minus n squared plus n divided by 2, and that's n squared minus n divided by 2, which is exactly what we get in here. So if we prove that the identity is a regular value of that map, it's over. Everything is true. The real analytic structure is derived from the fact that F is a real analytic submersion. That's it. So let's go. What we have to show is that the differential, we have to show that the identity actually is a regular value. So we have to show that the differential of the map F at A is surjective for every A in the preimage of the identity. In other words, for every A in the orthogonal group. Okay. But what we have is that if we consider f of A plus B, that's going to be A plus B times A plus B transposed, and this is A plus B times A transpose plus B transpose. We are trying to figure out what is the expression of the differential of F at the point A. And this is going to be A times A transpose plus A times B transpose, but plus B times A transpose plus B times B transposed. And the terms that are linear in B are these ones. So that's going to be actually the image of the differential of F at A applied to B. Okay? What we are going to have is that this differential is going to be A times the transpose of B plus B times the transpose of A. Okay? That's what we just said. And we have to check out that this map is surjective. So let's point out that the differential is a map between the tangent space to the set of square matrices, which is already a vector space, so the tangent space is going to be itself, to the tangent space to the set of symmetric matrices. But again, symmetric matrices are also vector space. So this map over here is a map between matrices and symmetric matrices. So what we have to do is showing that if we actually consider a symmetric matrix, then it's always in the image of the differential. Okay? So if we fix A in the orthogonal group, it suffices to solve the equation B times the transpose of A plus A times the transpose of B equals C for every symmetric matrix C. If you are able of doing that, then that implies that this map over here is surjective for every A in the orthogonal group, and in particular, the identity is a regular value, and we are done. So let's do that. We have actually reduced a problem that is not so easy, as our problem is showing that the orthogonal group is a real analytic differentiable manifold. We reduce that to a problem of linear algebra. So since A is invertible, because A is an element of the orthogonal group and every orthogonal matrix is actually regular, we can define B in this way. As the product of C, the transpose of A, and then we divide by 2. And let's see if B actually satisfies the equation. We have this expression, B times the transpose of A plus A times the transpose of B, but we can write it down in, let's say, interesting way as B times the transpose of A plus the transpose of such matrix. Of course, by our choice, B times the transpose of A is C divided by 2. And here, we have to consider the transpose of such matrix. So it's going to be the transpose of C divided by 2. And that's the moment in which we're going to use that C is symmetric. So the transpose of C is equal to C, and C divided by 2 plus C divided by 2 is C. So we show that the differential of F at any matrix in the orthogonal group is surjective. And this proves the proposition. Okay? In this lecture, we define submersions and then we study their properties. Indeed, we use them in order to show that the sphere of any dimension or the orthogonal group of matrices are real analytic manifolds. In our next lecture, we are going to provide a very interesting example of a manifold that it is actually built in an abstract way, but that can be realized as a real analytic manifold by using the properties of submersions. Thank you for your attention.